Hey students, we're going to look at some exponential and log models here. This is where we get into the why these things are used and where they become really useful in life outside of the classroom. The first thing we're going to talk about is dealing with radiation. And we talk about radiation with regards to things called half-lives. Half-life is the amount of time that it takes for something to degrade so that only half of it is left. And if we've got a 90 milligram sample, so I'm going to say that at time 0, we'd have 90 milligrams. I don't even know what, so they're calling this M for mass, I think. Okay, so 5 years, that means 5 years later, we'd have a mass that's half of this, so 45. 5 years later, this would be cut in half again to be 22.5. I don't know why I wrote 5 there, I meant to write 10. 5 years later, we'd be cutting this in half again and get 11.25. And we can keep doing that forever. However, we now know kind of how to work with equations. We have two ways to deal with this. The first is we can treat this as y equals ab to the x, like some of the ones we did when you're graphing exponentials. And when we do that, we can try some of these things. So 90 is equal to a times b to the 0. Okay, that's going to tell me 90 is equal to a. And then if I try my second one of these, we've got 45 is equal to, we said a was 90, times b to the 5. Okay, I'm going to divide that by 90 to get a half. And that gives me the fifth root of a half is b. It's kind of a gross number. But okay, I can kind of work with that. My equation for this would be y is equal to 90 times the fifth root of a half to the x power. That's doing everything in one step. Another alternative would be to think about this as a time divided by how long a cycle is, how long the period of this option is. And because we're being told that this is a half-life, b is going to be a half. A is always going to be that starting amount. So that would be 90 times a half. Our time is what we don't know, so I'm going to leave that as time. And our half-life, the period it takes to have half of this left, would be 5. That's the length of one cycle. Either of these two different versions of the equation end up meaning the same thing. One of them involves a gross fifth root of something, which is okay. And the other one is written as kind of a weird fraction thing. I like the way this one looks. So we've got y is equal to the starting amount, 90, times the rate, half for half-life, time divided by 5, because that's the amount of time it takes to be one cycle of this. All right, 6 months, we're talking about years here. So that'd be t equals 0.5. Y is equal to 90 times a half. 0.5 divided by 5 is going to be 0.1. Whatever that comes out to as a number is the mass of the sample. I'm going to rewrite that equation. So we had 90 times 1/2 t over 5. All right, for the first 20 years, so we know that this is going to be at 90, and that at 5 years, 1, 2, 3, 4, 5, cool, so right in the middle, it's going to be at 45, and then at 10 years, it would be at 22.5, so that would be like that. At 15 years, it would be at 12.25, and our graph is going to look something like this. gradually going down towards 0. The nice thing that we can do here, because getting to 0.1 milligrams seems like that would be kind of hard to do based on this graph, is that we now have logs that we can work with. So if I were to plug that into my equation, I want to get my weird stuff by itself, so we're going to divide by 90. So 0.1 divided by 90, because we all want to do that problem, is equal to 1/2 to the t over 5. When I convert this to log form, we get log base 1/2 of 0.1 over 90 is equal to t over 5. Multiply 5, and we get 5 log base 1/2 of 0.1 over 90. You've got calculators, you've got Desmos. You can do that calculation without having to do that by hand. All right, so now we're looking at some bacteria, and we're doubling every 90 minutes. So the first thing that I notice, so if I think about this as some kind of initial amount, is my A. That's that 800. Okay, so 800 B of T for bacteria is going to be 800. Doubling is going to be my rate. That B part is my rate. So that's going to be times 2. And then we're going to keep T as our variable. And every 90 minutes is going to be our kind of cycle time. That's that P thing. Cycle time. After 8 hours, oh man, but that's 90 minutes. So maybe I'll convert 90 minutes to hours to make that a little bit easier. Okay, so now I'm going to do this after 8 hours. We've got 800 times 2. 8 divided by 1.5. You can put that in a calculator. That will give you some answer. And that's it. All right, for the first 10 hours, cool. So let's set this up. I'm just going to do T and B of T. My equation was 800 times 2 to the T over 1.5. I'm going to do this with some easy to see things. Wow, 50,000. What? That's crazy. Okay, so we've got 1.5 is a nice number because that gives us just 1. We'd have 1,600. 3 hours. 3 divided by 1.5 is 2. And then we got 2 squared is 4. 800 times 4 is going to be 3,200. Hey, that's interesting. So if I go to 1.5 again, so that's 4.5, 6,400. 6 hours would be 12,800. Okay, now we're getting some big numbers. 7.5 hours. We're doubling that again, so that's 25,600. And at 9 hours, we'd be doubling that again, so 51,200. So we're somewhere like this. We said 7.5 was 25,000. I think that's going to be like there. We said 6 was 12,800. 4.5 is 6,400. Then we got 3,200 at 3. 1,600 at 1.5. Cool. I'd like you to notice this is... There we go. This is a nice exponential curve. This is a great example of where these things come into play really well, which is kind of a tricky thing. How long ago did this have 50 bacteria? So we'd say this is 50 is equal to 800 times 2 to the T over 1.5. Divide by 800. So 50 over 800 is equal to 2 to the T over 1.5. I'm going to convert this to log base 2 of 50 over 800 is equal to t over 1.5, and then multiply that 1.5 to the other side. So we get log base 2, 50 over 800. And again, you've got access to calculators and Desmos and all that fun stuff, so you can get the decimal for that. I went to the wrong page. In terms of log models, my favorite use of them is with earthquakes, because we have to use a log scale, because earthquakes have such a range in power. Ones that you can barely feel, that's going to be what we call a threshold amplitude, which is this 10 to the negative 6 number. That's this A sub-zero thing, to ones that can destroy cities. And those are billions, in some cases trillions of times as strong as one that you can barely feel. Living in Danvers, you may remember, this is probably 8 years ago at this point, there was a really minor earthquake that basically, if you were in some place that was kind of rattly, you heard like a thump or like a truck was going by very quietly. That compared to much larger earthquakes is a really insane amount of power that's going on there. Okay, so an earthquake has an amplitude of 10 to the negative 2. That's my A. 10 to the negative 6 is my A sub-zero. So I'm going to rewrite this as M is equal to log, this is base 10, 10 to the negative 2 over 10 to the negative 6. All right, I know based on exponent rules, this is going to be log of, I don't even know why I just wrote that fraction bar. I just want to use that thing that was on the page that I now can't delete. Oh no! I know I can delete that somehow. There we go. And when we do that, negative 2 minus negative 6 is 10 to the 4th. Log base 10 of 10 to the 4th power is going to be 4. So the magnitude on the Richter scale would be a 4. And from my recollection, that's an earthquake that you can feel. Depending on the length of it, it can cause some structural damage, but they aren't the ones that you read about causing severe damage in cities around the world. To check my units, it is going to be in meters. And was the first one that we did. Nope, we did 10 to the negative 2. All right, so now we've got a magnitude of 5. So I'm going to write 5 is equal to, and that's log. We said that A sub-zero was equal to 10 to the negative 6. So I don't know what A is in this case. That's what we're trying to figure out. 10 to the negative 6. And let's solve this. Okay, this is log base 10. I know to solve logs, I've got to convert this to exponential. So you've got 10 to the 5th is equal to A over 10 to the negative 6. And if I were to multiply this to the other side, we get 10 to the negative 1 is equal to A. So if we think about this, I think this is in meters, if I'm correct. I'm actually going to bounce back. This earthquake would cause this to move 0.1 meters, so 1/10 of a meter, which is somewhere on the order of a little bit more than 3 or 4 inches. So that's a significant amount of movement. If you're thinking about a seismograph is basically a pen on a stick, and it does this, and as the earthquake hits, it goes like this, and then resumes kind of the background sound, the background movement. Causing that pen to move 3 or 4 inches is going to be a pretty big jump. All right, 2 earthquakes have a magnitudes of 4 and 5.5. Am I correct in saying that? Okay. Oh no, we did. That was 4. So this would be A is equal to 10 to the negative 2. 5.5 we haven't done yet, so let's take a look at that. 5.5 is equal to log base 10 of a over 10 to the negative 6. We get 10 to the 5.5 is equal to, that's going to be a over 10 to the negative 6 after I've converted. Multiply that to the other side with exponent rules, that becomes 10 to the negative 0.5 is equal to a. And the ratio, I'm going to take those two and divide them. I'm going to use the 5.5 on top. So we get 10 to the negative 0.5 over 10 to the negative 2. And we get 10 to the 1.5. What that means is that earthquake has an amplitude that is 10 to the 1.5 times as large as the other earthquake. 10 to the 1.5 is somewhere between 10 and 100. The next example of where we use logs is going to be dealing with sound. Volume is based on a logarithmic scale because of how much louder some volumes are than others, and that makes it a lot easier for us to work with. This log scale is going to be a little bit different for us in terms of where these numbers come out. So this loudness is how loud we hear the sound. The intensity is how much vibration that sound causes. If you haven't had physics yet, sound is caused by vibrations in the air, and we hear that as those vibrations hit on our tympanic membrane in our ear, which causes our nerves to interpret those sounds. And this is the units that's measured in. This is watts per meter squared. Watts is a unit of power, and is really talking about how much power is hitting you as you kind of listen to things. So 10 to the negative 12, that's a really, really quiet sound that we can barely hear. And we're going to compare that to 10 to the negative 6, which is just kind of normal conversation with a not loud person. So let's take a look at this. We've got loudness is equal to 10, and then we've got log of, it's going to be 10 to the negative 6 over 10 to the negative 12. I'm going to rewrite that 10 log, and based on exponent rules, negative 6 minus negative 12 is 10 to the 6th. We know that this is log base 10, and 10 to the 6th power is going to be 6. So this is going to be 6 times 10 is 60 decibels. All right, now working backwards. So we've got a rock concert that's 110 decibels. That's the loudness. And now I'm going to do this as 10 log. We don't know what that I is. And then we've got 10 to the negative 12 on the bottom. Okay. I'm going to divide by 10. And we end up getting 11 is equal to log base 10 of that I divided by 10 to the negative 12. I'm going to then convert this, so that's 10 to the 11th power is equal to I over 10 to the negative 12. And now I'm out of room. I'm so sorry. I'm going to go up. When I multiply that over, we get 10 to the negative 1 is equal to I. So that would be a power level of 0.1 is the intensity. We can look at this in terms of trying to figure out how loud sounds are compared to each other. So this is, again, using that same thing. So 10 log, we've got I over 10 to the negative 12, and that's equal to decibels. When we plug in 85, that's going to let us solve this thing. So I'm going to call it loudness, and then solve this equation. So I'm going to divide both by 10 to start off. So we get 8.5 is equal to log base 10 of I over 10 to the negative 12. converting, we get 10 to the 8.5 is equal to, sorry, I forgot my I there. I divided by 10 to the negative 12. Multiplying that over, that's going to give me 10 to the negative 3.5 is equal to I. Okay, that's my first intensity. My second one is going to be 105, so I'm going to divide by 10. 10.5 is equal to log base 10 of I over 10 to the negative 12. All right, so we get 10 to the 10.5 is equal to I over 10 to the negative 12. That's going to end up giving us I is equal to negative 12 plus 10.5, negative 1.5. Finally, the ratio. I'm going to take my bigger volume, so 10 to the 1.5 negative, divide by my smaller volume, 10 to the negative 3.5. Using exponent rules, I'm going to subtract those exponents, and I get 10 to the 2, which is 100. That means that a sound that is 105 decibels is 100 times as loud as a sound that's 85 decibels.